So what's in the water? 99.98% hydrogen and oxygen. So probably not a surprise, but it's interesting to look at the numbers. That red sliver there is representative of everything that we find in the water that's not hydrogen and oxygen. It's called total dissolved solids, or salinity. Most of what we find are the salts that dissolve from the minerals into the water. That sliver represents about 250 parts per million. A part per million is one drop in an aquarium, kind of desk-sized aquarium. 1 part per million. Most of that, or half of that, is bicarbonate. It dissolves not only solids, but gases. So air dissolves into the water as carbon dioxide, and it forms carbonates when it combines with calcium and magnesium, which occurs in the sediments that leach into the water. So the other half are these minerals: calcium, magnesium, sulfate, sodium, chloride, even fluoride. Fluoride occurs naturally in our sediments. It occurs naturally in our water. And it's about at the optimum, there's a range that the dentists are looking for, and it's right at the lower level of that optimum level without adding any fluoride. A lot of areas add fluorides in other areas, but it's natural. In fact, some areas of our valley have too much fluoride. Close to those faults, the fluoride can exceed the drinking water standard. So there's a good example of something that they want some of that in there. It's beneficial, but not too much, then it's harmful. So you have to be in that sweet spot. And we find that by locating our wells in the right locations. And then there's these trace levels of sediments, again, naturally, that leach into the water, that you probably hear most about. You probably hear a lot about the arsenic, and you might hear about chromium, maybe uranium. Well, those things occur in our sediments, they occur in our water, but in the part per billion range, part per billion. One drop in your typical swimming pool, 1 part per billion. Very low levels. And again, with the instruments now, we can see these things. They've always been there, but now we start to see them, and then we start to see if there's a problem with them. So then we started treating the water. So before 1990, pumped the water out of the ground, into the pipes, everything was great. The regulators developed a new regulation for bacteria called the total coliform rule, and as a result of that rule, we started to disinfect to comply with it. So we add a little bit of chlorine to the water, typically several drops for a gallon if you compared it to. It's about 0.2 milligram parts per million. Your pool is about 1.5 to 2 parts per million. So just a fraction of what you would find in a pool. About half people can detect it, about half can't at that level. It's right about at the detection level. It kind of provides a safety blanket out there in the pipes, primarily to meet the standards. And we started that in 1990. And then more regulations. The arsenic, we had an arsenic rule since the 1960s. And some new data in Taiwan and Argentina where they were drinking hundreds of parts per million of arsenic, parts per billion of arsenic. And they saw some health effects. So they developed a new precautionary standard, very conservative. So it lowered that standard from 50 parts per billion to 10 parts per billion. Well, arsenic occurs naturally, mostly down in the East Valley, again related to the geology of that area, the faults, in levels that were slightly above the 10 part per billion new standard. So we had to enter into, for the first time, have to actually remove something from our groundwater to comply with the standards. So we installed, did a lot of research and installed water treatment plants down at 3 sites to treat about 5% of our water that was affected by that new rule. And currently, we're looking at a possible new standard for chromium. We expect a draft rule maybe this summer. And again, chromium is a naturally occurring sediment. It occurs in our water here. It's always been there. And so that's something we'll be watching closely. And who knows, maybe in the future, we'll be doing surface water treatment. Most of the country uses rivers and lakes, water that occurs on the surface, as their water supply. And you run it through a treatment plant, goes into the pipe. So we don't do that yet, but that's always an option. And it certainly is a very effective way to provide safe tap water also.
Is it true that they say after the water improves over blocks?
Yeah. True for things that can volatilize, and the bacteria is also our friend. Bacteria can eat away some of the organic matters and things that they can turn into, like nitrogen products. They can turn it into nitrogen gas. It goes up into the atmosphere. However, there are microorganisms. So the typical stream, I would be most worried about Cryptosporidium and Giardia. There are a couple of microorganisms that occur from the wildlife that uses those streams. So, if you're out there and that's all you have, by all means, you have to survive. But there is a greater chance that there might be those organisms that are going to give you diarrhea, and you'll recover from them. But they. Well, we can also build up antibodies, so our body gets accustomed to those microorganisms by developing other microorganisms in our guts, and then they can deal with those microorganisms. So you're right, if that was the only source that you drank from a young child, it wouldn't be a problem, because you would have built up microorganisms that could address that. Yes? Okay, chromium is an element, and an element like calcium and magnesium, and it's in the metal family of metals, and it's actually an essential nutrient. You need chromium to regulate your blood sugar levels. You probably see it on the side of a supplement, chromium perchlorate. Well, that's chromium 3. And your body needs that. In fact, our bodies are built to convert other forms of chromium to chromium 3 because that's what we need. We're always constantly looking for that. So our saliva, our stomachs reduce forms of chromium to chromium 3. You saw the Aaron Brockovich movie. That's chromium. So we know a lot about chromium from occupational exposure studies. When you inhale hexavalent chromium, it's not like drinking it. You absorb it into your blood system in your nasal passages and in your tongue area, and it goes into your bloodstream as chromium 6, not chromium 3. Your body doesn't deal with that the same way when you inhale it. So there's lots of data on the concerns and the health effects, typically lung cancer and tongue cancer, when you work in a factory inhaling chromium 6 dust. They knew a lot, for years we've known that. Well, now they're looking at whether ingestion might cause a problem. And since we're talking about it, I'll point out what we have here. They use rodent studies for that work. Science is not always, they don't always have all the information. So currently for chromium, they know it's a threat at inhalation, but not for ingestion. They just don't know that for sure. There's no human data to point to. All over the world, they've looked, and they can't find anything that really says, aha, that's a problem when you drink it. So they use rodents to do a test. And these are some of the water samples that have been set up with chromium added, just like what they gave to the rodents. And at the lowest concentration that they gave to the rodents is 5,000 parts per billion. This is far above anything that you'd find in a water source, but that's what they used for this rodent test. And at the lower concentrations, they had no health effects. The rodents drank, the rats and the mice, drank this amount of water for their whole lives. No increase, they survived as well as the control. They had no increased tumor formation. There were no health effects. But when they got up to the higher levels, 90,000 parts per billion and down to 30,000 parts per billion, they saw slightly increased, statistically significant increase in tumors. So they said, well, there you go. It's a carcinogen. And that's what all the news has been on, and that's why the state is looking at developing a standard for that. And it's based on this rodent study. And I'll talk a little bit more about how these regulations are set. Pardon? Oh, I'm sorry. I should have mentioned that. When chromium dissolves in water at high concentrations, it gives the water a yellow color. So, none of us would drink this water, but that's what they wanted to use for the rodents, because if they fed them lower levels, they wouldn't see any effect. And in toxicology, the number one principle is the dose makes the poison. Everything is a poison. It's all based on the dose. Calcium, everything you need essentially in your diet. If you get too much of it, it will kill you. Everything. So that's just common toxicology. So to me, this is just an experiment in toxicology. You give them too much and you have problems. So how they're using that for regulation is something that I think we need to improve on. I think we can do better than that. Oh, how'd we get there? Okay. Also here, I'm showing a chart. The regulations are increasing. You hear a lot about them, so they're constantly, right now they're looking at about 30 new ones that might, increase this chart. So we got to keep up with those regulations. So water treatment, we were talking about water treatment. This is what, in today's dollars, about $8 million will buy you. This is one of the water treatment plants that we installed down in Mecca, California. That's, if you're not familiar with the valley, it's kind of on the northeast edge of the Salton Sea. And that's down near some faults where we have that naturally occurring arsenic. These are sediment filters. We don't want particulates to enter into the facilities inside. So what's inside? Inside the treatment plant, there's a lot of vessels and pipes. We did a lot of research to find a technology that would not only remove arsenic, but remove chromium too, because we're anticipating a new regulation for chromium. We didn't want to spend all this money on one treatment technology that wouldn't address chromium that may be regulated in the future. Looks like that's going to pay off if the regulation comes. Here's a chart that shows the naturally occurring chromium, about 9 parts per billion in the water coming into the plant. And here's the treated water coming out of the plant down in almost no detectable chromium. So very effective. The rest of the country is very interested in this because this is the first plant built to remove chromium to a certain level from drinking water. And it's still the largest. So we have a lot of interest from EPA, and the California regulators are very interested in the effectiveness of this plant. Here we're seeing this process. These vessels are filled with a resin that absorbs ions. And ions are chemicals like arsenic and chromium, sulfate. After it's absorbed to a certain amount, you have to regenerate it by running it through a salt solution. The salt solution absorbs what you removed from the water, so the arsenic and the chromium's in the salt. This part of the treatment process then addresses that salt water. We can't dispose of the salt water, so we have to treat it first. So we concentrate the arsenic and the chromium and other ions into what looks like rust. And this is primarily iron. The iron absorbs to the arsenic and the chromium and you end up with this sludge. This has to go off to a special waste facility. And then the clean salt water can be put in a truck and driven to the ocean and put it in the ocean. So it's a very expensive process. This triples the cost to deliver that water. at this plant. We have that process, but that process may not work for chromium all throughout our valley because we do have variable water quality considerations. So we joined with the Water Research Foundation, a national organization, got some matching funds, and we're doing some research, first time for some of this. And this is a typical well site again. And here we've installed a pilot research facility where we take a little well water, we run it through these test columns, and we do tests on it to see how effective the different types of resin might be for removing arsenic. One of these test columns was, we were the first to test it. The University of Arizona developed an absorption media that we're testing. It didn't work too good, but they're still tweaking it. But it is fun and interesting to be able to be on that cutting edge. And the district has been proactive in that area to ensure that we can be leaders in providing the best water quality for our customers.